right, let's go ahead and talk through these. So what are you looking for in the periodic table? What piece of information or what about the periodic table tells you the charges? What are you looking at? Yes, you're right. So we're trying to look at the numbers of the columns in the periodic table because those help us understand, first of all, if we're dealing with a metal or a non-metal, and metals typically have what kind of charge? Positive charge, which means they did what to their electrons? Lost them, right? And so the column can tell us how many electrons it lost, and if we know how many electrons it lost, it can tell us the charge. So the opposite of that would be our non-metals. Non-metals typically have what kind of charge? Negative, and how did they get the negative charge? They gained electrons. It's a little harder to use the column number to figure that out, but if you work backwards from the noble gases, it does work. So looking at magnesium, magnesium is in column 2A. We know that magnesium is a metal. If it's in the second column, that means that it lost 2 electrons. When it loses 2 electrons, what's its charge going to be? Yep, 2 positive. Okay, what about aluminum? Where can you find aluminum? What column number? 3A, so you kind of have to go to the other side of the periodic table. Aluminum's still a metal, so we still expect a positive charge, so it should be 3 plus. Any questions about why aluminum's positive, even though it's on that right side of the periodic table? All right, K stands for potassium. Potassium's in the first column, so we would expect this to just be +1. Sulfur is a nonmetal, so we're going to expect that to have a negative charge. What column is sulfur in? 6, okay? So we know that it has 6 valence electrons. It's going to want 2 more in order to get to that noble gas configuration and have 8 valence electrons. If it has 2 extra electrons, what do we expect its charge to be? That's it. And then fluorine, because it's in group 7, we'd expect to have a charge of easy enough. Questions? All right, let's do something useful with that. So looking at problem 2.59, again, using the periodic table, now we're giving you 2 different elements, and we're trying to figure out how they're going to fit together. So again, go ahead and take 30 seconds to start on that. I'll walk around if you have questions, and we'll go through it.
Okay, so looking up gallium in the periodic table, we can see that it is in group 3A underneath aluminum. So we know that it is going to have a 3 positive charge. And we know that fluorine has a -1 charge, so that means when we put it together, we're going to need 1 Ga and 3 Fs, so that we have enough negative charge to cancel the positive charge. If we go ahead and name that, that's just going to be gallium fluoride. Since gallium's a transition metal, we should use the Roman numeral. Since it had a +3 charge, that's going to be a Roman numeral 3. And again, the IDE ending tells us that that's just a normal anion in an ionic compound. All right, next one, Li and H. So they're both in the same column, which initially is a little strange, but we're going to go ahead and make an ionic compound here because we know that lithium is definitely a metal with a +1 charge because it's in that first group. Now, hydrogen can have a +1 charge, but it can also have a -1 charge when it's acting as a nonmetal, and that would make this LiH. And the name for hydrogen when it's acting as a nonmetal, when it's an anion, is hydride. So that same IDE ending. So we've got lithium hydride. So someone pointed out that this looks like it might be an acid, so it's a good catch on the fact that there's hydrogen there, but when we have acids, that hydrogen is going to be with other nonmetals, so here it's not acting as an acid, so that's why we just have lithium hydride. Okay, next one, aluminum and iodine. So we know from before that aluminum is 3 positive, iodine is in the same column as fluorine, so it's just going to be 1 negative. So this is going to look very similar to the gallium-3 fluoride. And the only difference is that aluminum is not a transition metal, so we don't need the Roman numerals. So this is just going to be Al(I)3, and we're just going to call that aluminum iodide. Okay, and then the last one is K and S. So K is potassium, that's in group 1, so that's just going to have a +1 charge. S is sulfur, that's in group 6, so we saw before, that's got a 2 negative charge. Now in order to make these fit, we're actually going to need to have more potassium than sulfur, because sulfur's got a 2 negative charge, so we need to make sure we have 2 positive things to balance that out. So the formula here is going to be K2S, and we're just going to name the pieces, so potassium sulfide. Again, notice that all of these end with IDE because we just have a single element. If we had an oxygen in there, then we could have something like sulfate or sulfite, but we don't have that at all, so we just need that normal IDE ending for ionic compounds. So they're telling us the reactants. We know that we're starting with Mg. What does the S after it mean? It just tells us that it's a solid. We know that we're reacting that with chlorine as a gas. Okay, and based on what you know about the different types of reactions, if they just say that it's going to be reacting two things together, we can assume that's what kind of reaction. Just a combination, okay? So the product is going to be some combination of magnesium and chlorine. Since we know magnesium is a metal and chlorine is not, it makes sense that they're going to form an ionic compound. So the typical charge of magnesium when it's in an ionic compound is +2. We know that because it's in the second column. Chlorine's -1. Oops. So it's going to be MgCl2, and we can probably assume that that is going to be a solid. All right. So now in terms of balancing it, we just need to make sure we have the same number and types of atoms on both sides. So I see 1 magnesium on the reactant side, 1 on the products, 2 chlorine on the reactant, 2 chlorine on the products. So do I need any coefficients? No, so that's it. So this one is already balanced when you just write it based on what chemicals are there. Questions about that one? All right, let's try the next one. Barium carbonate decomposes into barium oxide and carbon dioxide gas. So barium has what symbol? Ba, which means it's in column 2, which means barium is going to have a 2 positive charge. What about carbonate? Can you find carbonate in the periodic table? No, it's a polyatomic ion, and there's a clue in the name. 8 at the end tells you that it's going to have that oxygen involved. So carbon-8 is exactly what it sounds like. It's carbon combined with oxygen. Anybody remember the formula for that off the top of their head? CO3, and what's the typical charge? Yep. So that means the formula here is just going to be BaCO3. So we've got a 2 positive and a 2 negative. We don't need parentheses or anything like that to balance the charges. Since it's undergoing a decomposition reaction, we just have that reactant, and it's decomposing into something else. I'm going to put a little triangle over my arrow. Why would I do that? What does that indicate? Heat. Heat. So you'll see that when there's heat involved in the reaction here. All right, so it's going to decompose into barium oxide. So barium oxide, again, is going to have barium in it with that 2 positive charge. And oxide is just what? Just oxygen. Okay, and the typical charge on oxygen? -2. So that is just going to be BaO. And we should be pretty familiar with carbon dioxide gas. So talk to me about how naming of carbon dioxide is different than barium oxide. Why is there a di in carbon dioxide? Okay, there's 2 oxygens, but how come I didn't call it magnesium dichloride before?
Molecular compound.
All right, so molecular compound, meaning it's made of only nonmetals, and that's when we use prefixes. So do remember that there's a difference between naming ionic and covalent, or if you call them molecular, that same idea, that there's prefixes here because there are no metals. All right, what about balancing? Anything we need to do to get that one balanced? Yeah, no, we're actually already good, so this is fine. And I'm going to go ahead and just assume that one is solid as well. All right, C is pretty rough, so we'll do that as our last one. Again, I'll give you guys about a 30-second head start, and we'll go through it. All right, let's go ahead and talk through this one. So they're telling us our starting material is styrene, C8H8. They're telling us that it's combusted in air, and combustion is a very specific type of reaction. Every time I undergo a combustion reaction, I start with a hydrocarbon, which is something that contains carbon and hydrogen, which is styrene. What do I always need for a combustion reaction? My second reactant is always oxygen, and that makes sense because we know that there's oxygen present in the air. When I write oxygen, I write it as O2 because it's one of our 7 diatomics, so even though it's just called oxygen, it's always O2. The products of a combustion reaction are always the same 2 products. Those are, water and carbon dioxide. Sometimes you'll get carbon monoxide, but that's an incomplete combustion reaction, and we're not worried about that. Okay, so now I've got the basic reaction written out. So just by looking at that, is that already balanced like the other ones were? Yeah, no way. So I'm seeing that I start with 8 carbons on the reactant side, but I've only got 1 on the product side. When I balance combustion reactions, I like to leave oxygen last. And the reason I do oxygen last is because the fact that it's present in the CO2 and the H2O can make it tricky to balance. So I fix it alphabetically. Fix carbons first, then I fix hydrogens, and sometimes the oxygens just take care of themselves. So in terms of fixing the carbons, if I have 8 on the reactant side, I need 8 on the product side. Now I'm going to fix the hydrogens. I have 8 on the reactant side. How do I get 8 on the product side? I need 4 waters. Okay, go ahead and take a minute to count up all the oxygens and see if we can figure out what sort of coefficient we're going to need on the O2. If I have 8 carbon dioxide molecules, how many oxygen atoms do I get from that? That's 16 oxygens. If I've got 4 water molecules, how many oxygens do I get from that? So I've got 20 oxygens on my product side. That means I need to have 20 on my reactant side. But in order to get 20 oxygen atoms, how many O2 molecules do I need? Only 10. Okay, so be careful with that.
And let's also go ahead and add the liquid for the C8H8 since they told us that it was a liquid.